Hi, my name is Fateh. I'm a PhD student in the Control and Power Group of Imperial College, the Department of Electrical and Electronics Engineering. And today I have the privilege of having an interesting discussion with Dr. Balarko Chaudhuri, who is a reader in Power Systems in the Department of Electrical and Electronics Engineering and Director of the Master's Program in Future Power Networks at Imperial College. His current research focuses on the dynamic stability and control of electric power grids with high shares of variable renewables and inverter-based resources to facilitate net zero transition. He is the UK Director of the Global Centre on Electric Power Innovation for a Carbon-Free Society, EPICS, which is pioneering the transition to an electricity grid powered entirely by renewable energy. He also leads the workforce development pillar of the Global Power System Transformation GPST Consortium that brings together key actors to foment a rapid clean energy transition at unprecedented scope and scale by providing coordinated and holistic end-to-end support and knowledge infusion to power system operators. Dr. Balarko works closely with the Women in Power System Transformation Initiative to promote gender diversity in the workforce and serves as an associate editor of the IEEE Transactions on Smart Grid, IEEE Systems Journal, and Elsevier Control Engineering Practice. So thank you for joining us, Dr. Balarko.
Thank you.
Yeah, I think my first question will be on the your role as the coordinator of the GPST teaching agenda. Just like I've said, the GPST is the Global Power Systems Transformation Consortium, and I understand that you had a role to, first of all, assess what the gaps are in knowledge and skill necessary for the energy transition, and then to create teaching materials around that and make those publicly available. So could you please talk a bit about that?
Yeah, this initiative actually began around 2021, which is when GPST sort of started. We did a survey of the power engineering curriculum at universities, well, across the world, I would say, but only looking at universities which are active in power. And we identified some gaps in terms of the topics which should be taught in the postgraduate program, but we thought were lacking at that point in time. So as a group of academics, it was a relatively small group involving about 7 or 8 universities from North America and Europe primarily. We identified about 90 odd topics, and these are forward-looking 90. Forward-looking topics which are essential for sort of power system transformation, but was lacking in the curriculum, and we felt postgraduate power engineer looking to sort of join the power industry should be aware of these stuff. So what I mean by topic is these are sort of bite-sized chunks. So each topic would typically have 3 to 4 hours of lecture and slide deck, exercises, etc. And we intentionally kept it bite-sized chunks so that universities can sort of pick and choose and embed them in their existing curriculum, because obviously it's unreasonable to expect that universities would overhaul their curriculum. And we started calling upon experts in the respective field to work up the material on these topics. So far, we have made a modest start with only 8 or so topics available on the GPST website. When I say available, it's the course material involving the slide deck, recorded lectures. But we have a long way to go, and we are sort of looking for funding to support these efforts to basically cover this whole lot of topics.
Yeah, I think that's a very useful endeavor. There's a lot of talk about the gap between academia and industry. So I think the GPST is doing its best to fill that gap. And it's a bit surprising that you could find up to 90, that's 90, almost 100 topics that are needed in the power systems industry, but not covered in the curricula in universities. Does that include Imperial? I'm surprised.
Well, I have to say it does. To some extent, we have to also do some soul searching within our own curriculum, and we are trying to incorporate some of this stuff within our own teaching. And I should also mention that, because you brought up the industry angle to this, so once this teaching agenda was developed, as I said, primarily by academics, what we did in order to road test this, we invited, if I'm not mistaken, 12 leading system operators from around the world, and this would include the 6 founding system operators of GPST.
All right.
And when I say leading system operators, these are system operators who already are seeing high penetration of renewables in their system.
Okay.
So we asked them to prioritize these topics
Okay.
under each of the 9 broad areas that these topics were bucketed in. And based on the collective weighting or priorities, obviously each system operator did that based on the skills gap that they see and the priorities they have in their own jurisdiction. So what we then did is we considered those views and identified 3 top priority topics under each area. So we have a list of around 27 to 30 topics,
Okay.
which we really want to develop the material on subject to funding so that we can sort of target our effort on the priority stuff. So at least these 27 to 30 topics have got strong buy-in from the industry,
All right.
system operators.
That's interesting. So the teaching materials that have been developed, where can they be found, accessed?
On the GPST website.
Okay.
GPST has got 5 pillars. So this activity is under pillar 3, which is about workforce development.
Okay.
That's led by Imperial.
All right. Again, the GPS is stands for Global Power Systems Transformation Consortium. The official website is globalpst.org. That's globalpst.org. And then these materials can be found under the 3rd pillar here.
3rd pillar, which is foundational workforce development.
Okay, foundational workforce development. That's interesting. One of the characteristics of the transition that's going on in the energy space is the penetration of inverter-based resources. So the first question is, what are inverter-based resources and how have they changed the electricity network in Great Britain, for example?
Most renewables or most variable renewables like wind, solar photovoltaic, these are resources which cannot be directly plugged onto the grid, unlike the conventional fossil fuel generation or some other forms of renewables like hydro generation. So these resources, because of the way they operate, need to be integrated to the power grid through inverters.
Okay.
And these are known as inverter-based resources, although there are other resources like battery energy storage, etc., which can also be sort of categorized under that term. How have they changed this? I mean, the basic change is moment you interface a resource, primary source of energy through inverter, the way they interact with the grid is driven predominantly by the control system of the inverter rather than the physics of the resource itself. And that has got a huge bearing on how the overall stability, dynamic stability of the grid pan out. And because in the UK and some of the other jurisdictions like Australia, Texas in the US, the penetration level of these inverter-based resources is getting to such level in terms of percentage of the overall generation. The stability problem is changing, and at times it becomes difficult to foresee some of these stability problems in the grid, which basically forces the system operators to operate the system in a conservative way. And one of the major implication of that is they might have to curtail renewables in a sort of overly conservative fashion, which is never good for decarbonization.
Yes, and to curtail renewables means to curtail. It means to turn off or to
not necessarily
utilize,
turn off,
or
but
to ramp down, right?
Operate part loaded. I mean, given a particular wind speed, if a particular wind farm could have been producing,
so you operate below capacity.
Yes.
And that has financial implications because there has to be some payments. You have to pay the owners of these wind farms to tell them to ramp down or to operate below capacity, and that payment eventually trickles down to the electricity bills of the consumers. So it's we invest so much to have the renewable farms, and then when we have to curtail them, we still have to pay the owners of those farms. So it's never good, right?
That's one thing, and also if you are generating less from the renewables, you have to make up from sort of other gas-fired generation, for example, which is again cost and emission.
Yes. So the presence of renewables renewables on their own currently, the technology is not able to run without some base load from traditional power plants. Okay, yeah, and again, I like that you mentioned the fact that first of all, there is a kind of race to net zero. There are climate targets all over the world, and the system operators that are seeing a very high penetration of renewable or variable renewable generation. I think the UK is probably leading the world right now in terms of the percentage of renewable generation, and that leads to unforeseen challenges. And many times we're having to deal with the effect of that. One of the unforeseen challenges is what is called sub-synchronous oscillations. I know you know quite a bit about it. We've had some instances in the United Kingdom, and I think altogether there have been about 19 examples of sub-synchronous oscillations around the world from 2007 to 2021. There was an example in the UK in 2019, another example in 2021, another example in 2023. And if you follow the progression, it means we're expecting another example next year. I hope not, in any case. So can you please talk a bit about what these oscillations are about and what causes them?
Yeah, I mean, sub-synchronous oscillations are not new. I mean, they existed even in the traditional power systems which was dominated by synchronous machines.
Okay.
For example, if you go back to 70s, when the sub-synchronous resonance came into being, which is oscillations happening in thermal power plant with multi-stage turbine shaft, and then that interacting with a series compensated line, which throw resonant frequencies at relatively low end of the spectrum. Again, I mean, there were sub-synchronous oscillations associated with synchronous machine-based power plants evacuating power through radial high voltage DC lines, which is known as sub-synchronous torsional interaction. So these things have been around and they're well understood and mitigation measures are in place. Since the sort of dominance of inverter-based resources in power systems, like you gave the UK example, where it's particularly north of Scotland, within a very tight-knit, electrically tight-knit area, there are lots of inverter-based resources.
Wind especially.
Yes, mainly wind. There are batteries coming up, etc. There are high voltage DC, which are also part of inverter-based resource family. When you have such a situation, the control system of these inverters tend to sort of adversely interact with each other through the network.
Okay.
And this is when the so-called system-wide sub-synchronous oscillation manifests.
Okay.
Now, for other types of sub-synchronous oscillations which are local in nature, like sub-synchronous resonance, sub-synchronous torsional interaction, even sub-synchronous control interaction with a particular kind of wind turbine interacting with a series compensated line, these are relatively localized phenomena, and it's again relatively easier to analyze because you know which components you're dealing with. But when this sub-synchronous oscillation is propagating across a broad area with multiple inverter-based resources interacting, one major challenge is to identify which one or which ones are causing the problem.
Okay.
And that is turning out to be extremely challenging because of multiple reasons. One primary reason is the control system of these inverter-based resources are proprietary and they are vendor specific, and for obvious reasons they won't disclose the detail of it. And without knowing what the control system is doing, it's difficult to sort of analyze which one is creating the problem. And hence any form of systematic mitigation to this problem is still something which is requiring active research and development.
Yeah, that's interesting. So I think for the sake of simplicity, I understand that when we talk about sub-synchronous oscillations, we're talking about oscillations first of all, and sub-synchronous means below the synchronous frequency, right?
Correct.
So if the synchronous frequency in the United Kingdom is 50 hertz, so usually because of the interaction of the control mechanisms in the in the electricity network, there could be oscillations at a frequency below that synchronous frequency of 50. And that's why it's called sub-synchronous oscillations. And again, I've heard you say it's not new. We've had sub-synchronous resonance. I think like you said, in the 70s, they've been there with synchronous machines. And I think based on the little I know about this, the difference is that those oscillations kind of occur naturally and they are damped naturally. I mean, they naturally attenuate until they just dissipate. But with inverter-based resources, sometimes we have them, instead of being damped, they are amplified. And then they are also as a result of interactions between the control systems of different inverter-based resources. And then it's difficult to, first of all, identify the cause of the oscillation and then to find a way to mitigate it. I was in a conference earlier this year and talking about damping of sub-synchronous oscillations, and there was a lot of... I raised the point that many people did not accept, which is that we cannot have a universal, or I think we cannot have a universal solution because to that problem, because we have to find out the cause of the oscillations, right? Could it be an oscillation coming from the interaction, coming from harmonics, for example, harmonic currents flowing within the inverters, which is not uncommon, or could this be as a result of, if it's purely an oscillation of power, then it can be damped with the use of a resistor, a pure resistor. But if it's an oscillation in current, then that's a bit different. So does that make some sense?
Going back to your first point about SSR, sub-synchronous resonance, being usually well done. Well, there have been cases where they had to deploy specifically tuned SSR dampers because they weren't.
Like power system stabilizers?
Power system stabilizers, you could in principle do that if you filter out the frequency properly through some sort of notch filter. But there are other forms of dedicated SSR dampers which are different from power system stabilizers. For the sub-synchronous torsional oscillations, again, it depends on a number of factors. For example, the rating of the power plant with respect to the rating of the HVDC link, the radial connection, I mean, if there is any bypass route to that. But again, I mean, for sub-synchronous torsional interaction, it's well understood, and there are indices which can quantify the potential risk of those problems happening. It's not that if you decide your rating of the power plant and the HVDC link without considering this rating, the oscillations will always be well damped. They could actually be negatively damped in the worst case, but thanks to those indices and a proper understanding of those phenomena, you can actually virtually eliminate the possibility of those during the planning stage itself with the current tools. And in an ideal world, this is where we want to be with inverter-based resource-driven sub-synchronous oscillation, which are not so much local. I mean, again, if it's local, it's slightly easier because you know what you're dealing with. But if it spreads across even, let's say, north of Scotland, which is not geographically huge, but if the oscillation spans from east side to the west side, from, let's say, Edinburgh to up northwest, you would have to point your finger to the potential troublemaker before you can.
And that's not very easy. I want to talk a bit about to bring it home to Great Britain. Like I said, there have been 3 occurrences in the last 4 years or so, right? So just before the blackout, the incident in August 2019, there were 9 hertz oscillations that were identified, and this caused an 800 megawatt wind power plant to deload to 60 megawatts. So this power plant lost over 90% of its had to ramp down 90% of its capacity. And there was a problem with the voltage control. So that just for the record, that was the blackout happened on the 9th of August 2019, when at 4:52 p.m. a lightning struck a transmission line, a 400 kV transmission line in Cambridgeshire, and there was a generation loss of about 2,100 megawatts, and a loss of supply to over 1 million customers. Right. So I don't know the extent to which those particular oscillations in that particular wind power plant contributed to the overall situation in August of 2019. That was probably a multivariate situation where there are many factors contributing, but then oscillations were identified. And then in 2021, in August, again in Scotland, there were 8 hertz oscillations in the RMS voltage. observed in Scotland. Again, just like you said, because it's an area with a lot of wind power. And then last year, between June and July, there were oscillations. I think from about 5 to 9 hertz. Most of them were about 8 hertz again, which occurred on 5 separate days in June and July. Right, there was no power outage, no demand was lost, but some assets had to trip. There was some generation that had to trip, an interconnector and HVDC link, and the transmission circuit also. Right, and concerning this, the ESO held an operational transparency forum on the 8th of November last year with regards to this, and it was said that the most likely cause of the sub-synchronous oscillations was identified in mid-July, and changes were made, and there have been no further SSO events until today. So it means this is a real issue. I try to read up a bit on the ESO's report from that event, and something about it is not satisfying because it sounds a little bit probabilistic. I understand that they took some measurements from PMUs, and based on that, they identified the most likely source of the oscillations, the asset that was most likely to be the source of the oscillations, and then they had the owner of those assets to do some internal testing and then make some modifications to their control, right? So. But it still feels, and the report doesn't give more specifics than that. I don't know whether it's because, for the sake of system security, they do not want to disclose all those details, or it's because we don't really know, like you said, because we have to deal with models that are black box models, and we don't really know exactly how to empirically identify the source and the cause of oscillations, right? So maybe you want to comment on some of these real life examples and what they would mean, because if this is something that can cause a blackout potentially, then it's a problem to worry about, isn't it?
Yeah, I mean, blackout is obviously the extreme outcome of this.
Definitely.
But even if there is no blackout which is specifically caused by this, there is a continuous harm in the way that in order to steer clear of these problems, the system operators are having to operate the system conservatively.
Okay.
Which means
more expensive.
Yes, more expensive, bad for the environment if you have to fire up the gas, keep the gas plants fired up.
Because we know them, we understand them, they're safer and more predictable.
Sure. Now, what we are trying to do, hopefully to get rid of this menace of sub-synchronous oscillation, we are working closely with National Electricity System Operator, formerly National Grid ESO, on a 4-layer approach. The first thing, obviously, it's can we design the control of these inverter-based resources in a better way so that the chances of these things happening is less. Of course, that's not NESO's territory. That's more of the OEMs, the original equipment manufacturer, or the developers. Then once the control is designed, let's say at some appropriate level, the first check where the risk of these potential oscillations will be captured would be the grid connection studies or the compliance studies. Now, at the moment, the way those studies are done is rather simplistic, and we believe, and we are working closely with NESO on this, whether we can make those connection compliance process a bit more rigorous to capture the risk. Again, it's not going to be foolproof because this is still a one-time effort when the IBR connects to the system, but then the system is evolving rapidly. So either you would have to repeat those connection compliance for each IBR at some interval to see if something else has changed. Yes. And then with that, so that's the second layer. The third layer is trying to capture the possibility of these incipient oscillations near real time or close to real time. Again, we are working on some sort of a digital twin framework to capture these things near real time and hopefully avoid them happening. And even if oscillations slip through all these 3 layers, the 4th layer would be the post-mortem. So if things or oscillations took place, can we develop a way to identify what caused the problem so that the system operators then can go back to the OEMs and ask specifically for mitigation at the right control loop or control level. So hopefully with this sort of cyclic four-layer approach, the sub-synchronous oscillations can be tamed at some point.
Yeah, I'm hopeful about that too. Speaking of which, speaking about the system connection compliance process that was released by the ESO, NESO, formerly officially ESO, earlier this year, I think they recommended about 4 different modes of small signal studies. Small signal studies, like a way to determine the stability of a power system, right? And I think they recommend step change EMT simulations, small signal injection studies, EMT active frequency scans, and then the eigenvalue method, right? Just to try to inject some oscillations and to see how the system under study behaves under such under such oscillations. And I think for at least 2 of them, or for most of them, they represent the AC grid as a Thevenin equivalent, and then the system under study is represented as an EMT model. But I think some of these EMT models really have to be simplified because we may not have the computational capacity to deal with the real models. And then I don't know how available the EMT models are for the kind of systems that we have to study. So are they really available?
Well, a typical connection compliance process, the study would be sort of a joint exercise between the OEM and the grid operator. Now, the OEM would obviously have the detailed model of their IBR, inverter-based resource control system.
Yes. They have it, but they won't release it.
They don't release it, but they would run the study with the grid model that is supplied to them by the grid operator like NESO. And the simplicity comes from that side, actually. It's the grid model which is, we believe, oversimplified to capture potential risk of SS. So, for example, you mentioned about Thevenin equivalent.
Yeah.
What is normally provided, at least for wind farm connection as of today, is a Thevenin equivalent at power frequency only, or synchronous frequency only. What we believe is it ought to be covering basically a spectrum of frequency, so the impedance over a range of frequency over which potential interaction can take place. And obviously, the operating point, a series of operating points are considered for this, so it would be a family of impedance spectra, so to speak. And then obviously the challenge is how are you going to decide on the extreme? What about the interpolation? What kind of studies you have to do? You mentioned about those 4, like step change, eigenvalue. Those are all going to be valid. It's just that the representation from the grid side would have to be more comprehensive to capture the risk.
It's very interesting. Yeah. So the system operator has to rely on OEMs to do the right thing, and the OEMs have to also be generous enough to help the system operators with enough information that they need. So it's very interesting what's going on, because we have this electricity grid that is very sophisticated and very impressive, I would say. It's a big machine. It's like, I think someone has described it as, we are flying a plane and we want to change the engine of the plane while still in the air, right? So there's a lot of collaboration that has to happen in this space. So we have a few minutes left, and I want you to maybe recommend a few research questions that you think are very useful in this area.
One is how you can do a stability analysis given the black box nature of these IPR models, because the source of this problem is really within those black boxes.
If we know exactly what's there, we have the right tools and methods to analyze it. But we don't know what's there, and we have to go around that somehow.
We do have some generic models of these IBRs, but then again, the parameterization of those generic models is a big issue. There's no one size fits all. You'd get some default parameters for the control loops, but it's not going to be catering for all the operating points, and how you get around that is it's one of the major research challenges that we are grappling with.
Oh, that's good. So to end our conversation, I'll just ask you a few questions. They're called Quickfire Questions, which means you're meant to answer quickly. I'll just mention a pair of kind of competing technologies, and then I'll ask you to choose the preferred one and maybe to give a reason for it. Right? I
Okay.
just have 4 of them here. And the first one is GFM versus GFL.
Well, that's a difficult one. I mean, everyone's talking about it.
Yes, it's kind of the AI right now in our space. GFM
Yes.
stands for grid forming, and GFL
Yeah.
stands for grid following. There are 2 different methods of inverter control, to put it simply.
Yeah. Well, I mean, grid forming is usually seen to be sort of the savior to some of these stability problems, although there are caveats to that. But I think one of the things that we need to keep in mind is which type of resource is sort of suitable to have grid forming operation. For example, I know there is serious pushback from some manufacturers about having grid forming functionality on wind turbines. Because grid forming, typically they act more like a voltage source
you
as
need a
opposed to a
strong
current
grid.
source. So, yeah, I mean, that's one of the things. And another is, moment you are trying to act like a voltage source, you are basically living at the mercy of the grid condition. So, for example, if there's a fault on the grid, it that jerk could be felt on the turbine itself. I'm not saying it is necessarily going to happen, but it's a possibility. Whereas if you're doing explicit current or power control, as they do in grid following, you're basically decoupling this from the resource side.
Yeah.
So that's a concern. I mean, so far the grid forming installations have primarily, or if I can safely say, all of the grid forming facilities are on batteries.
Okay, yeah.
With batteries, there's no problem as such, and also batteries you typically operate such that you have margin either way.
Yeah.
But if you were to have grid forming on other resources, you will have to first of all keep that margin, which means you have to sort of spill some amount of power, unless you are operating part loaded anyway. I'm talking about operational ready condition. But one of the major concerns is associated with wind turbines on the potential impact of a grid event on the mechanical side, basically.
Yeah, so it seems these technologies are not competing; they are actually complementing technologies.
correct.
For now,
Yes.
they have to go together. Okay.
Absolutely.
Nuclear energy versus wind turbines.
Oh, okay. Yeah, I think a lot of that has to do with the perception. Some countries are have been historically very rich in terms of nuclear, and unless you have some sort of a bad event with nuclear, they are flourishing with clean energy source. It's very friendly with the grid. It's well understood. Obviously, with technologies like wind, because of all that we discussed, there is this potential risk of adverse interaction, oscillations being just one of them with the grid.
Okay.
So, yeah, I mean, both are clean. Nuclear at the moment is obviously it's proven, understood, more grid friendly.
Yeah.
Wind, hopefully, with all the research and development going on, would be as grid friendly, and then they are both good. Again, coexist.
Okay. HVDC versus HVAC. HVDC is high voltage direct current. It's a
Yeah.
way of transmitting energy from one point to another. And then HVAC is high voltage alternating current.
Yeah, I mean, again, this debate has been going on for ages, over a couple of centuries.
Yeah,
I would
maybe as
say.
old as the debate
Yeah.
between AC and
Yeah.
DC, right? The war of the currents.
Yeah, I mean, HVDC is more favorable for very long distance overhead transmission, as well as subsea transmission beyond, I would say, 100 kilometers, just to take a number. So the need for interconnection between geographical region is growing because to exploit the geographic diversity in renewables. For example, I mean, there are going to be massive cable links between UK and our neighboring countries. There are already several cable links. There are going to be many more.
Okay.
For example, to exploit the hydro generation in Scandinavia, solar generation in the Iberian Peninsula, and so on. If wind is not blowing in the UK on a particular day, we can have those cable links importing power. And similarly, the other way around. If there's no sun on a particular day in Iberia, they can sort of import wind power from UK. So interconnection at a massive scale is essential to security of supply in a renewable dominated regime, and HVDC is going to play a huge part in that.
Yeah. Yeah. So HVDC is superior when we have to send energy across distances that are more than 100 kilometers. I
For
think
cables.
that's for cables.
And for overhead lines, it's much longer, but then in countries like China, India, Brazil, where there are very long distance transmission routes, more than 3,000 kilometers available.
That's
Again, I mean, HVDC
superior,
has one
okay.
obvious advantage.
And finally, energy storage versus demand response for frequency stability.
Again, I mean, the short answer to that, Fetter, would be they would have to coexist, each bring their own value to it. But there is an extent to how much you can do with these things. So, again, they will be complementing.
Yeah, demand response, I think, has been talked about for decades, but it has not taken off as would have been expected, because contrary to what people think, changing the behavior of the entire population is very difficult. Very difficult. I mean, so making someone get up to do the laundry at 2 a.m. it's not as easy. It's easy on a simulation, but in real life, it's not very easy.
But with sort of electrification of transport and heat, there's going to be more potential on that front to do something. Again, I mean, I'm no expert on this, but I have heard colleagues saying that even buses flying around in big cities could be a source of flexibility to the grid. So
that would be interesting to see.
Yeah. I think managing this would be the key.
Yeah, definitely. Dr. Balarko, thank you very much for
Thank you very much, Feta. It's been a pleasure. Thank you.